Okay, so today, we're just largely going to be review lots of stuff that we were talking about in Math 102. But I think for many of you, it's probably been a while since you've looked at some of these topics. And obviously depends on whether the intermediate math courses between, first year and now, whether any of them were proof space. So for example, if you've largely done, actually, what are the prereqs for this class technically? Do you all have to have taken like 224 or something? I don't remember exactly, but yeah, okay. So 102, 224, 202. Okay, so there's like a secondary intermediate proofs course somewhere in there, right? Yeah, 240, absolutely. So presumably, there's been another proofs course, but who knows, some of you might be fourth year and, haven't taken a proofs course in a while. So we're going to do a little bit of review. Now, the first thing is mathematical induction, because believe it or not, induction is somehow going to show up in group theory. But hopefully you've done like induction so many times now that we don't need to spend too much time on it. Again, let me just kind of review what I think are the important high points. So the idea of induction, I like the domino model. Basically, you're trying to prove that some proposition is true for all n, right? So our goal here is to prove that P of n is true for all natural numbers. Okay, with some obvious caveats that maybe you're not actually proving it for all naturals, maybe you're proving it for all naturals greater than or equal to 7, or maybe you're proving it for the naturals greater than or equal to 10, or maybe only the even naturals, whatever. The only thing you really need is some ordered discrete set, right? And therefore, it's actually possible to transcend just the integers and do this on much bigger sets. So the entire idea about how induction works is you prove the following. All right, so how this works. So what we end up doing by the induction hypothesis, we prove this chain of equivalences. Right? This is what the induction hypothesis gives us. Or rather, the induction step. That's step 2 here. So we've proven that pk implies pk plus 1 for all k. And so we can chain those together. So p1 implies p2, right? That's when k is equal to 1. p2 then implies p3. That's when k is equal to 2. p3 implies p4, and so on and so forth down the line. Which means that the moment we can prove one of these statements is true, all of the statements to the right of it is true as well. So if we prove this true, then all statements to the right will also be true. Right? That's the whole point of this implication arrow. You prove P of 1 is true. That tells you P of 2 is true, P of 3 is true, P of 4, and so on and so forth. Right? So that's the whole power of induction. So it allows you to prove a statement Pn is true for all possible n. Okay, so let's do an example. Again, you've probably done a million of these. I think the example that Ali chose is to do some sort of summation. I'm not going to do a summation. Let's do something a little bit different. So let's do this as an example. All right, so let's say, suppose that F is a map from A to B. Show that for any collection, maybe we'll say finite collection. Of sets, that the following is true. A1, AN. Oh, let's do union. Okay, So what I want you to do is actually take 5 minutes or so here, and of course ask as many questions as you want in the chat, or you can jump on mic if you want. And I want you to take a second and actually see if you can prove this true. Is this the sort of thing people have seen in 102? Because I know, for example, we talked about unions and intersections, and we'll talk about images there, but I'm just trying to wonder if anyone's actually proven this before. Like, does this seem familiar? Okay, well, then that's great, right? So we can prove this. And probably some of that depends as well on who your instructor was, right? Because they might choose to do different examples. Okay, great. So, I mean, if there's a possibility that you've seen it before, phenomenal. And then if not, then this will be new, right? And remember, is everyone okay with what I mean by F of a set, right? Like we remember that that's the image. Maybe let me just rewrite that in. So recall, oops. All right. Or maybe this is a nicer way of writing it. So it's, one way you can think about this is it's the range of the function if its domain were just the set A, right? Like that's how you can think about the image. Or alternatively, it's the collection of all things that F sends A to, right? So let's see if we can prove that. Again, let's take 5 minutes or so. And again, please don't hesitate to ask me questions, and then I'll take it up and we will see exactly how it's done. Okay, so I'm going to give you about 1 more minute, but if you think you need more time, just let me know. Okay, so I'm going to talk about this a little bit. So if you need a couple, a little bit more time, you have it, because I'm just going to ramble for a bit. But these sorts of things are common, where we kind of say, oh, look, the base case here, for example, is going to be show that the image of the union is the union of the images when there are only 2 sets. And then inductively, we're going to expand that to an arbitrary but finite number of sets. And a lot of the time, you'll hear us say, especially in upper year classes, we'll prove it for 2 sets, and we'll be like, and of course, this naturally extends to, arbitrary finite numbers of sets. And I think probably some of you would have seen this in like 240 or 224 when we are doing things like direct sums, and we prove something on the direct sum, and then we like prove that it holds for an arbitrary number of direct sums, sort of thing. So we use this a lot. It's the sort of thing that you should probably go through once to convince yourself what the argument is. But then once you've done it once, you can kind of relegate it after that to, oh yes, I know, clearly this should work, and I don't have to kind of prove it again thereafter. That being said, of course, if it comes up on a test, you actually prove it. So first thing that we're going to do, right, is we're going to prove the base case. Okay, so in this case, the base case is actually n equals 2. I mean, the n equals 1 case is trivial, right? Because f of a1 is equal to f of a1. There's nothing really useful there. So in this case, we're not actually going to prove this for all natural numbers, or I guess we are, but the interesting base case that we need to consider is going to actually occur when n is equal to 2. And we're actually going to explicitly need the n equals 2 case a little bit later on in our proof. So let's try it. So let's show. So we want to show that f of a1 union a2. Actually, you know what? Let me put that on the next line. F of a1 union a2 is f of a1 union f of a2. Okay, and again, anytime you're doing proofs, write down what it is you want to show. It always helps to have it in front of you to just kind of remind you of what it is that you're doing. Okay, and in order to do this, we're trying to show an equality of sets. We're going to have to do a double subset inequality. So let's start with this direction. Okay, so let's pick some element on the left-hand side. So let's say let's take B to be in this thing, right? Now, since B is in the image of A1 union A2, if we look back at the blue, which tells us what is the definition of the image, that means that B is equal to f of A for some A in A1 union A2, right? That's what it means to be in the image of A1 union A2. You look like f of something where that something is in the union. Now, of course, since A is in the union, it's in one of those sets, right? It's either in A1 or A2. And this isn't the sort of thing where you want to break it into cases. What we'll just say here is, without loss of generality, let's assume that it's in A1. So without loss of generality, assume A is in A1. Now, I know that a lot of the time you've probably heard the instructor at the front of the room say, without loss of generality, is everyone okay? Like, now is a time when I want to make sure everyone in the room is all right with what without loss of generality means here, because of course it's going to be said a lot, and especially in this class, because again, it's a Proofs class, right? So what I'm trying to say here is, listen, it's either in A1 or A2. If it's in A1, great, we're going to continue with the proof. If it's in A2, well, this is just a naming thing. Let's just basically rename A2 A1 and continue on with the proof, right? Like, it makes no difference which of these sets it's in. So we're just going to assume it's in A1 because we could just rename them if we really wanted to. Okay, so hopefully that makes sense. And if not, throw something in the chat and I can kind of elaborate on it a little bit more. But don't do this in cases. Just assume it's in A1. Okay, so because it's in A1, then that means that B is actually in F of big A1, right? Because B is equal to F of little a, but little a is actually not only in the union, it's actually in big A1. So that means that little b is in big F of A1. And thus, if you're in one of the sets, you're certainly in the union. Okay, so that does one inequality because we started by assuming that B was in this side, and then we proved that it was in this side, right? So that gives us one inequality. The other inequality I am going to actually leave. But it's almost the exact same thing. It's like basically you're just going to reverse these steps, right? You assume it's in F of A1 union F of A2 without loss of generality. Assume it's in the first one. Well, if it's in the first one, then it looks like F of A for some A in A1. And so, yeah, then it's in F of A1 union A2, right? It's exact same steps basically, but just reversed. So I'm going to leave that one because I don't think that there's a crazy amount of stuff there. But are there any questions about that? So that's just the base case. We're going to do the induction step. I think the induction step is actually easier than the base case. But if there's any questions about that, don't hesitate to scream out and let me know. Okay, so far so good. All right, so for our hypothesis, right, we're going to assume that P of n is true, i.e. we're going to assume, and at this point, hopefully everyone's okay with this. I'm actually going to use a little bit of notation just to make my life easier, so I don't have to write out a million unions. Like this. Okay, we've seen notation similar to this, like sigma notation. If you've done, in 224 or 240, you've probably seen a direct sum notation like this. So it just means, take the union over all of the things on the right. So we're going to assume that this is true for n and now show it for n plus 1. So suppose that we have n plus 1 sets, right? A1 through an plus 1. And now we're going to see why that n equals 2 case is really, really useful to us. What I'm basically going to do, and again, this is kind of the generic step that you always do here, is I'm going to smush A1 through AN down into a single set, right? So I'm going to define A hat, maybe, to be A1, the union of A1 through AN. So that when I take the image of the union, well, before I actually do anything, I am going to rewrite this as just a hat union AN, right? Because the first n of those things is A hat. Now, by the base case, right, I know that that actually splits into F of A hat union F of AN like that. Now, I haven't used the induction hypothesis yet, but if I re-expand out what F of A hat is, oops, oh, sorry, that should be AN plus 1 everywhere. Sorry about that. AN plus 1. Like so. Oh yeah, sorry, Carmina, thank you. You're right. I missed the plus 1, and I didn't see it in the chat. But luckily, I did catch it myself. And now I am going to use the induction hypothesis because I said, listen, I know that by the induction hypothesis, a union of n sets splits across the image. So I'm going to use that now. This is the induction hypothesis right here. A1 union F of AN union F of AN plus 1, like that, right? Let me clear that, write that a little bit nicer. Like so. Voila. Right? And so this is what I'm saying. You can imagine that you could do this with other things. Like I said, direct sums interestingly work. Let me ask you the question though, does anyone think that this is true if I change union to intersection? Like, is it true? Is it false? What do we think could go wrong if it's false? Or do you think that if we went through with the proof, we'd be able to get it? Does anyone think it's true for intersection? Or maybe let me phrase it a different way. So here's just kind of like a bonus thing. And this is pretty important, right? You should know whether this is true or not. So let me say f of the intersection. Okay, so the question here is, what do I put here? Right, do we put subset equals, superset, equal sign? Or can we say anything? Does anyone have a guess? Okay, equals. Yeah, okay, so there's an equals guess. Like, just guess, right? If you don't know, just guess. Subset, not equals. So Brian, you're saying like we can't say anything? Is that what you mean by not equals? Subset makes sense. Okay, subset. Okay, so here's the interesting thing. So some of you think subset, some of you think equals. So first of all, I would encourage you all to try this. But off the top of your head, for those of you who say subset, can you give me an example of a function in sets where it's not equals, right? Where it's a strict subset, because if that's the claim, right, that it's subset, then you're basically saying they're not always equal. The best we can guarantee is a subset. So give me an example where these two things are not equal. Okay, I just give you like 60 seconds because I'm not too worried about this. It's kind of a fun little exercise, but yeah, let's see if you can come up with something. That's true, right? If the intersection of two sets is empty, then their image will be empty. Yeah. Right. That's actually a really great way to set up counterexample, Hector. Yeah. So good thinking. So how can you? So now though, you probably want their images to somehow intersect, right? So that even though they're in the domain, they might have an empty intersection. When you take f of them, they overlap in some way, right? So this is actually a really clever idea. So can you think of a function which does that? Surjective, sure. X squared might work, Justin. I mean, but like what sets? What are? Give me two sets, A1 and A2, where this is going to happen. Because yeah, I think you can do it. Okay, yeah, but be more specific. Like, give me like an interval, say. So we kind of want to take x squared, right? So let's say f, let's just map r to r, right? Let's not be complicated. Takes x to x squared, set a1 to be, okay, sure, yeah, -1, 0, and 1, sure. Let me take Hector's, which is almost the exact same, but that way I just don't have to write out 0. -1, a2 is equal to 1, right? So this is going to be a counterexample to equals, right? Because we get A1 intersect A2 is the empty set. So f of A1 intersect A2 is also the empty set, but f of A1 is equal to 1 is equal to f of A2. Right, so they're not equal, then we do get subset, right? So absolutely, oh, sorry, I want the intersection on the outside. Intersect f of A2 is equal to 1, right? So we do get subset, right? Now, of course, that's not a guarantee that subset is true, right? We'd still have to prove that, but as a bonus thing, if you just want to give it a shot, try proving that the subset is true. I'll confirm for you that it is true, subset is true. And then if you really want practice, again, try and do the induction proof like we did up above here, right? To show that the image of an arbitrary finite intersection is a subset of the intersection of the images. And you'll see that like this probably isn't worth doing a second time because the steps are almost identical, right? And so it's the sort of thing that like once you've done it once, you can very quickly be like, oh yes, I can see how I can always take, like if I have a binary operation, I can always extend it to any finite combination without needing to worry about it. And the proof is technically by induction, but you know, it's kind of not worth playing out every single time. Okay. So are there any questions about that? Why wouldn't this proof not work for it? Okay, there's a lot of negatives in there, so I have to parse it out. So why wouldn't this proof not work for infinite sets? So it's not infinite sets. I'm not worried about whether the sets themselves are infinite. I'm worried about whether or not you have an infinite collection of sets, right? So you'll notice here that the proof or the statement is that it has to hold for A1 through AN, right? And not A1 ... And there's an infinite collection of sets. And it's not, I'm not saying that the result is false in that case, but you can't prove, you can't use induction to prove things about infinitely many things, right? Induction doesn't work that way. Because if you look at the domino chain here, up at the beginning, P1 implies P2 implies P3, so on and so forth. This chain allows you to prove something about any Pn, but it doesn't allow you to prove something about like P LF naught or first countable infinity sort of thing, right? So induction will only let you prove things about Pn where n is finite, not where n is infinite. And there is something called transfinite induction. That's a little bit more complicated, but that's not covered by this induction, right? So if you want to do the proof for infinitely many sets, like the union of infinitely many sets, you have to do the proof slightly different. Induction doesn't work. But you know, that's kind of an interesting thing. Does anyone know how to even define the union of infinitely many sets? Right? Does anyone know how to do that? It's in some sense the obvious thing, right? Like you would take a union of infinitely many sets and you would just say, this is the collection of things which are in at least one of these, in one of the things I'm unioning, right? But most of you, I think, when you're thinking about taking a union of infinitely many sets, you're thinking about probably a countable union, right? Like you have sets A1, A2, A3, A4, and so it's a countably infinite. But what's to say you couldn't have a real number's worth of sets that you're unioning, right? What happens if you have an A sub x for every x in the real numbers and you want to union those together, right? You can still do that, but you have to be a little bit more complicated about how exactly you're thinking about things. So if you want to explore that, that's a really cool avenue to go down, and I really promote that and suggest that you try it. I don't think it's anything we're going to worry about too much in this class, but if you're interested in ask me questions later too, and we can go over it. Okay, so equivalence relation, that's a 102 thing for sure, right? We talk about relations, we talk about equivalence relations, and in particular, we talk about, you know, how equivalence relations partition sets and these things in 102. Now, I can't emphasize enough that this is the time, this might be the first class that you've taken where this stuff is going to be crazy important. There is a reason why we're reviewing this. So let me begin by prefacing this with the following question. I think in 224, we don't generally do quotient vector spaces. I know I didn't last time I taught it. But for those of you who took 240, did you do any quotient spaces? Does that word sound familiar? Okay, you did do quotient spaces? Okay, so maybe it depends on who you took 240 with. Some people, I think it's kind of ends up being an optional thing where some people will cover quotient spaces and some people don't. So if you've taken quotient spaces before, you know this notion of equivalence relations. Right. So we're going to do a lot of quotients in this course, and quotients are all about equivalence relations. So I can't emphasize enough, if you weren't comfortable with equivalence relations the first time you took them, you're going to have to, and it's worthwhile to spend some time, more so than induction, okay? Honestly, if the question is between studying induction, excuse me, and equivalence relations, study equivalence relations, because we're going to do a lot of equivalence relations in this class. You really, really, really want to be comfortable with that, okay? And if that's scary, I hope it's not. They're a little bit, it takes a little bit to wrap your brain around, but once you get it, they're not too bad. Okay, so we know that an equivalence relation on a set, right, has to satisfy three properties. It has to be reflexive, right? So the elements have to be related to themselves. It has to be symmetric. So A is related to B and B is related to A, and then transitive. So if A is related to B, B is related to C, then A is related to C, right? And in fact, maybe let me, the three notions here are written as reflexive, symmetric, and transitive, but maybe let me rewrite them in beside using the notation that we would normally do, right? So we'd say that A is similar to B, or sorry, A is similar to A. We would say that A is similar to B if and only if B is similar to A. And then maybe black was a bad choice. A similar to B and B similar to C implies that A is similar to C, right? That's what these three properties are when you translate them into using the equivalence relation notation. Okay, and the idea is to capture the idea of equals, right? That's what an equivalence relation means. Think about the word equivalence. We're kind of trying to capture the idea of two things being equal. And of course, the equal sign satisfies all three of these properties as well, right? A is always equal to A. If A is equal to B, then B is equal to A. And if A is equal to B and B is equal to C, then A is equal to C. So we're trying to capture those defining properties of what it means to be, for two things to be equal, okay? So let's play around with this a little bit. Now, this one I'm going to follow very similar to what Ali did. I'm going to present it in a slightly different way. So the example I want to work with here is the following. I want to be a little bit concrete to start with. So let's say example. So we'll say that two integers A and B are related if there exists another integer such that B minus A is equal to 3K. Okay, so we're going to say A is related to B if their difference is equal to 3 times a number. All right, so show that this is an equivalence relation. I don't think this one is as hard as possible in the induction. So again, I want you to try it. I'm going to give you 3 minutes this time to give this one a shot, and then we'll take it up. So here's the definition, play with it, and let's just make sure that we're comfortable with that. Okay, so 3 minutes. And again, don't hesitate to throw in the chat if you have any questions before I take it up. Okay, so hopefully you've given this a shot, and hopefully you managed to do all three properties. I think 1 and 2 are probably pretty easy. 3 isn't too bad, but of the three properties, it's definitely the one that requires the most work. And this is pretty much universally true. Anytime you're trying to prove that something is an equivalence relation, 1 and 2, reflexive and symmetric, are usually really easy, and it's the transitive property that involves the most work. Okay, so let's give it a shot here. Let's see how that goes. Get rid of this thing. All right, so solution. All right, so first thing, reflexive. So we'll say let's say fix some k in z. Note that k minus k is equal to 0, which is certainly 3 times 0. So k is similar to itself, right? That's what it means to be reflexive. Everything is equal to itself, equal. In this case, we subtract the two things, we get 0. That's definitely a multiple of 3, right? No problem. Okay, symmetric. So suppose that A is similar to B, and then let's prove that B is similar to A. So if we suppose that A is similar to B, that tells us that there is an integer such that B minus A is 3k, right? That's the definition of what it means for A to be similar to B. Now I want to do is show that B is similar to A, right? So I need to show that A minus B is a multiple of 3. But A minus B is just the negative of B minus A. And that's definitely an integer multiple of 3, right? So B is related to A like that. Okay, so that's reflexive and that's symmetric. The only thing we have left is transitive. Now, again, like I said, transitive is usually the hardest. In this case, though, there's really only one thing you can do. Like if you set everything up correctly, then you'll be like, oh, okay, there's only one way I can put these two pieces together. And again, if you didn't see this, it just might be that we need to flex the proofs brain a little bit, but that's okay, right? It's one of these nasty things where we have to add and subtract magical quantity just to make things work out, which is why I kind of consider these ones to be a little bit trickier, right? So in this case, we're going to suppose A is similar to B and B is similar to C. So there exists, let me call them M and N this time. M and N such that B minus A is 3M and C minus B is 3N, okay? And again, always do this. Anytime you're proving anything, you're like, okay, I know A is similar to B, B is similar to C. I'm trying to show that A has to be similar to C. Take a second and unravel what those definitions mean. And don't just unravel them, put them on the piece of paper in front of you. I can't emphasize this enough. And I know that this is probably boring to some of you because you feel comfortable with proofs, but this is for the people who maybe aren't the most confident in their proofs. Don't try and have those things in your brain, because when they're in your brain, it's easy to not be able to get the whole picture. Make sure that you write them down. So what is it we're trying to show? We want to show that A is related to C. So we want to show that A is related to C, right? And again, I'm even going to write down what that means. You obviously don't have to, i.e., that is that C minus A is 3k for some k. Okay, and here's what we've got. We've got this bit of information and this bit of information, right? These are our only assets. These are the only things that we have access to. And I need to say something about C minus A. Okay, so when I'm proving this, what I say to myself is, okay, I want to say something about C minus A. Both of the things that I've circled in yellow, though, or squared off in yellow, have a B inside of them. So I need B to show up for me to be able to use those things. So this is why I say it's one of these tricky things where we're going to add and subtract B. It's because I need B's. Both of those yellow things have a B in them. So let's add and subtract B in just so that we get it, right? Just so that it shows up. Right, so I haven't done anything crazy. I've just added in a 0. but I'm going to re-bracket these. And again, this step really isn't necessary, but I'm going to re-bracket this just so we can see exactly what's happening. And voila, what do you know? Now we have B minus A and C minus B. Those are exactly the two things in the yellow squares. And lo and behold, we're good to go, right? So setting K equals to M plus N does the trick. And there we have it. We've now shown that this is an equivalence relation. Okay, so any questions about that? Is everyone all right with that? Good. So, I mean, one question too here, like this equivalence relation has a name. The way that we normally write this down is we write this as, we say A is congruent to B mod 3. I think this is definitely something that was brought up in 102, right? Is it okay to reverse the conditions on A and similar to B? Well, I mean, ultimately we showed that it's symmetric. So depending on what you're asking, Karina, like we showed that it was symmetric, so it doesn't matter if A is on the left or B is on the left. So definitely, if we were to change the conditions around like that, it doesn't end up making a difference. Does that answer that question, or did I just misunderstand what you were asking? Okay, perfect. All right, so we write this, right? So we write, so instead of writing A is similar to B like that, this has us, this one shows up enough in mathematics that we give it a special symbol. We write A is congruent to B mod 3. Okay, and some people don't put the brackets around mod 3. They might just write mod 3. And that's what that means. Now, hopefully, if you think about what we just did in proving reflexive, symmetric, and transitive, you can convince yourself that there's nothing special about the number 3 here, right? If I'd replaced it with the number 5, certainly reflexive and symmetric are true, right? Like those proofs aren't crazy at all. And you can imagine if I replaced 3 with 5, it's just literally in the proof everywhere where there's a 3, replace it with a 5, and the exact same proof goes through, right? So there's absolutely nothing special about the number 3 here. About the number 3. Right? We could have done this for absolutely any, let's say, positive integer. Right? So that gives us this notion of A being congruent to B mod N. Okay, now if you're not 100% convinced by that, and you might not be, and that's totally okay. If you're not 100% convinced by it, go back, do the proof, but now do the proof for an arbitrary N, right? So basically, up here in yellow where it says B minus A is equal to 3K, replace that with B minus A is equal to NK, or if you want, you could replace this with, so this could also be written as 3 divides B minus A, right? If you're more comfortable with the divisibility notation, you can change it so that N divides B minus A, or that B minus A is equal to NK, and redo the proof if you want to. And you'll see the proof is word for word identical, just everywhere there's a 3, you put an N, okay? But like I said, if you want a little bit of extra proof, and maybe even if you didn't get the transitivity property there and you just want to reaffirm that in your brain and give yourself a little bit of extra practice, go through it, but this time do it with a different number, okay? All right, so we're going to do a little bit more about this. So modulo, right, this equivalence relation of A being congruent to B mod N is crazy important. So it shows up not only in group theory, but also a lot in number theory. And I think I mentioned last time that there's this like weird an unfortunately unavoidable relationship between group theory and number theory. Like they're actually really closely intertwined at least in the early days with discrete group theory. So we're not going to be able to avoid that. Same sort of thing. Like in your readings, you probably noticed that the GCD came up a lot and the Euclidean algorithm and all these things. And, like I said, we can't avoid that. That stuff's actually going to be important. Okay, but let's do another quick one. So show that for all k in z, k squared, no, let's say odd, for all odd k in z, k squared is congruent to 1 mod 4. Okay, so let's try that. Again, I'm going to give you probably about 3 minutes to do this. I don't even think that this is a 3-minute thing, but I'll give you 3 minutes just in case, and we'll see where you get on that. And if you have any questions, you can throw them in the chat, but I'm just going to run and fill the coffee maybe quick. Okay, so I don't remember how long I've already given you. I was going to give you 3 minutes. I think we're about 3 minutes. Let me take this up. And I know that, we're in a 2-hour lecture today, so I'm going to take a break here, but let's take this one up. And then what I want to do is I actually want to post the next one, and then I'll give us like a little bit of a longer break to both, take a break and work on that problem. Okay, so that's our idea here. So we want to show that if I give you an odd integer, that it's congruent to 1 mod 4, right? Always congruent to 1 mod 4. And that's probably like not something that's immediately obvious, right? Like often you kind of have to think about this, and you try it out. You're like 3 squared is 9. Oh yeah, that is congruent to 1 mod 4. 5 squared is 25. Oh yeah, that's also congruent to 1 mod 4, right? That's a cool thing that works out. The solution really doesn't end up being too bad at all. So solution, right? So if we want to write down an odd integer, the way we often do that is to write it as 2k plus 1 for some other integer k. So let's say well, I've already used k. Let's use a different thing. So let k be an odd integer. And write this as let's say m. K is equal to 2m plus 1 for some m in z, right? Anytime you're dealing with even or odd, if it's even, write it as 2m. If it's odd, you write it as 2m plus 1. And this gives me something to work with now, because if I want to square this, I'm just going to square 2m plus 1. All right, so we get k squared is 2m plus 1 squared. And if we work that out, somebody double check my math. We should get 4m squared plus 4m plus 1, right? So yeah, again, I'm pretty sure that I did that right. Or is it? No, it is 4m. Okay. So now, if you're thinking about like, if I want to show that this is congruent to 1 mod 4, what I'm saying is, well, clearly the first two terms are divisible by 4, right? They're congruent to 0 mod 1. And then the only thing left over is that extraneous 1 term. So this is definitely going to be congruent to 1 mod 4. Or alternatively, so I would be perfectly fine if you just immediately at this point said, this is clearly congruent to 1 mod 4. Right? Since the first two things are definitely congruent to 0 mod 4. But if you really want to be pedantic and you're like, okay, well, hold on, that wasn't the definition. I need to show that 4m squared plus 4m plus 1 is congruent to 1, i.e. that their difference is divisible by 4. Then you could go through that. You would say, oh, and we have 4m squared plus 4m plus 1 minus 1 is 4m squared plus 4m. Right? And that's what you wanted to show. So 4m squared plus 4m plus 1 is congruent to 1 mod 4, like that. Okay, any questions? Ooh, hot coffee. Hopefully that's not too crazy. Again, I think like some of this stuff is review, and I wouldn't feel bad if you don't remember some of this stuff, or maybe it's entirely possible that some of the stuff is like, oh yeah, I remember doing that. I think I could pick it back up, but maybe I'm a little bit rusty. That's okay as well. But now I'm going to give you something. I don't think this is a 102 type question. I think this might be a little bit too hard for 102. But on the other hand, we're all third year now, right? So I think we're allowed to be a little bit harder than 102. So what I'm going to do is I'm going to post this question up. So exercise. Show there are no integer solutions. To this equation. Okay. Now, one last thing might help before I let you go for a little break. So in this problem, I said, look, the square of an odd integer is always congruent to 1 mod 4. Very quickly, can anyone tell me what is the square of an even integer congruent to mod 4? Okay, so if you were to do the same proof, yeah, it's 0, right? Yeah, exactly. Great. So the square of an even integer is always congruent to 0. The square of an odd integer is always congruent to 1. So no matter what integer you have, it's always either congruent to 0 or 1, right? Mod 4. When you square it, the square of an integer is always congruent to 0 or 1 mod 4. And that's going to be a little bit helpful. So I want you to think about how would I prove this? And the hint is to use this previous question, okay? Use the fact that the square of an odd number is congruent to 1 mod 4 and the square of an even number is congruent to 0 mod 4 in order to prove this. So here's what I'm going to do. Normally in a 2-hour class, we might take a 10-minute break, but then I'm also going to give you 5 minutes to work on this problem. So I want us to we're going to take a 15-minute break here. So it's about 2:10 now. So we'll come back at 2:25. And then at 2:25, I will take up this problem, okay? Yeah, that's 3c squared. Maybe let me write that a little bit cleaner. 3c squared, like that, okay? Hopefully that's more clear. So at 4 or 2:25, we'll come back, we'll take it up. So take a 10-minute break and then spend about 5 minutes trying to work on this problem as well. Okay, again, throw some stuff in the chat. I'm gonna go and refill my water and stuff, but I'll be back relatively shortly and we'll be happy to answer any questions that you might put in there. But 2:25, okay? So let's meet back here then and we'll take this up. Okay, so we're gonna come back here real quick. Let me preface it before we actually get back into it by saying I do think this is a 102 question in the sense that I've seen this done in 102 before, or at least something like it. And as kind of pointed out in the chat, right? The way you would have done this in 102 is to say, let's go through all the cases where A is even, B is odd, C is even, something like this, right? And that even through that reduction, sure, it's not 8 cases, maybe it's 7 cases or whatever the case might be, but that's a lot of work. And what I'm trying to illustrate here is the power of modular arithmetic, right? What I said is we want to really use the result that we just did, which is that the square of an odd number is congruent to 1 mod 4, and the square of an even number is congruent to 0 mod 4, because I claim that with that piece of information, you can immediately determine that the only way this could have a solution is if A, B, and C are all even, right? So hopefully if you went through the cases, you came to that conclusion anyway. But let's think about, why this would be true. So let's just start by looking at the right-hand side, 3c squared. There's only 2 possible things. If we work congruent, or if we work in mod 4, the right-hand side, 3c squared, can only take on 2 values mod 4. What are they? Okay, that would be for c squared, but what about 3c squared? 0 and 3, exactly, okay. So the right-hand side is either 0 or 3. Okay, now the left-hand side is the sum of two things, which are both either 0 or 1, right? So the question is there any way for the left-hand side to be 3? Right, it's not possible, right? The left-hand side can't be 3. It's either 0, 1, or 2, right? So the left-hand side is either 0, 1, or 2, which means 3 is not possible. So both sides have to be 0. Okay, and there's only one way for the left-hand side to be 0. That's if both A and B are congruent to 0, i.e. both A and B are even. Nice, right? That's way easier than doing 100 million cases, right? So we're immediately able to conclude that A and B and C are all even. Okay, so does that make sense so far? Like, we're not done, but I want to make sure that everyone has understood the reasoning so far and why the power of modular arithmetic can be used to like really simplify the number of cases that we might have. Okay. So just comparing what the right-hand side can be and the left-hand side can be, we immediately conclude everything is even. Now, once we know everything is even, we're going to do our usual thing by saying, okay, let's write A is equal to 2m, and B is 2n, and C is 2l, something like that, right? So let's write A is 2m, B is 2n, C is 2l, like this. And then let's plug this in and see what we get, right? We're hoping to eventually arrive at a contradiction, right? Because the problem says show that there aren't any solutions. So I guess, I've been a little bit sloppy here, but what I've said is what I meant to say, or should have said in the very beginning is, assume there is an integer solution. So if we plug all this in, what are we going to get? So we're going to get 2m squared plus 2n squared is 3 times 2l squared. And of course, you can expand all of this out, but we're going to see that everything definitely has a factor of 4 in it. So by the time we cancel everything out, we'll get this equation. What can we immediately conclude about this equation? M squared plus n squared equals 3l squared. Anyone? Yeah, everything has to be even, right? This is exactly the same equation as above. So if m, n, and l satisfy this equation, they all also have to be even. So by the same reasoning, are even. Okay, why is this a contradiction? Or at least it's not immediately a contradiction. There's nothing saying I couldn't do this, but why is this going to lead to something which is absurd? Anyone see it? Like, what happens if I were to say, okay, right, m is 2i, n is 3 or 2j, and l is 2k? Yeah, you just keep going, right? And eventually what you get is like you never actually, basically what you get is you can just keep dividing whatever a, b, and c are, you can divide them by 2 as many times as you want, right? Like, no matter what you do, you can always keep dividing them by 2. Effectively, what you want to be able to say is, and you could do this in a long way if you wanted to, but again, I think it's comfortable to say it here. But if you want to rigorously prove it, you can. Effectively, if we continue this process, then we can show that 2 to the k divides a for all k. And that's not possible. Okay. In fact, if you want to do an induction proof, now is a great opportunity, right? So what you would do is you'd say something like, okay, suppose that this equation, a squared plus b squared equals 3c squared, suppose that it has a solution. Claim 2 to the k divides a for all natural numbers k, right? Base case is basically this, right? When you proved that all of the numbers were even, go by the induction hypothesis, argue that eventually you get back the same equation, right? Which adds the extra power of 2 on that you want. So if you want to try and practice a little bit more induction, here's a cool place to try it if you wanted to do this formally. But I would say it would be okay saying like, look, clearly this is ridiculous, because if I continue to do this, then I can just keep taking I divide it by 2, I get a new number. I divide it by 2, I get a new number. Divide it by 2, I get a new number. And eventually, right, that process has to stop. There's no number that can be divided by 2 an infinite number of times, right? So you arrive at a contradiction that way. But like I said, if you want to be formal and you want to practice your induction, then that might be something you can do. Okay, so I think that would actually be kind of interesting and a little bit of fun to give it a shot. But are there any questions about that? Like, does that make sense about like where the contradiction is? Again, my first line of this should have been assume there is an integer solution. I'm sorry, I forgot to put that in. But you can insert it if you want. Everyone's okay? That makes sense? Okay. So, and of course, we're just kind of like flying through the various topics that we need to in terms of Math 102. This is like Math 102 crash course, right? We're doing like 6 weeks of material in 2 hours. So the last thing we're going to talk about injection, surjection, bijection. And again, this shouldn't be, it's certainly not new. I know you've all seen this in 102, 202, 240, whatever the case might be. But again, we're really, really going to start using them, right? In notions of injections, bijections, and surjections. Bijections especially are going to come up a lot. I think a lot of you in your linear algebra, right, you learned about isomorphisms. And you knew that, for example, isomorphisms of vector spaces are linear bijections, right? And if you think about that, it is basically a bijective map which preserves the interesting structure of a vector space, namely vector addition and scalar multiplication. And we're going to have the same sorts of things when we talk about groups, right? We're going to be interested in bijective maps which preserve the group structure, and those are going to be called group isomorphisms instead of vector space isomorphisms. So bijections as well going to end up being super important, but it will be also notable to talk about just injective functions or just surjective functions. They're definitely going to come in. All right. So we can kind of breeze through, I think, the definitions pretty quickly. We know that you're injective if you are effectively 1-to-1, right? That the only way that f of x is equal to f of y is if you actually started with x being y in the first place, right? You're surjective if your range is equal to your codomain. So if everything in your codomain is hit by something in your domain, and you're a bijection if you are both left and right, or sorry, I'm getting ahead of myself. You're a bijection if you're both injection and a surjection, right? Okay, so classic, we know that those things are true. Now, the way that I want to practice this is let's actually bring up, let's do some things. I think that these things would have been done in 102 as well, probably again, depending on instructor. So they might be new or they might not be. But let's start off with the following. Okay, so suppose, I love this one. This is one of my favorites. So suppose that what I want here, f maps B to C, and G maps A to B, and F composed G is injective. Show that G is injective. Okay, this one's pretty important. So let's start off with that one, give that one a shot. And again, it shouldn't take too long. But let me know if you've seen this one in 102, right? So in the chat, let me know if you're like, oh yeah, I'm pretty sure I've seen that question before. Okay, so our goal here is to show that if I have a composition which I know is injective, then the inside function itself also has to be injective. All right. And this is one of those problems where you say, if you just set it, this is one of those problems where if you set it up correctly, again, there's only one thing you can do, right? So suppose the g of x is equal to g of y, like that. We want to show that x has to be equal to y. And again, there's only one thing that we know, right? There's only one asset that we have, which is namely that the composition of f and g is an injective function. So if I want to be able to use that fact, f composed g should show up somewhere. So what I'm going to do is post-compose with f everywhere. So acting on this with f gives us f of g of x equals f of g of y, like that. And we know that f composed g is injective. So if I get that f composed g of x is equal to f composed g of y, then that tells us that x is equal to y. And that's what we wanted, right? We started with g of x equals g of y, and that told us that x had to be equal to y, and that tells us, therefore, that g is injective, right? And that's not like, it was literally a one-line proof. Now, you may know injective and surjective are dual in the sense that often if you know one thing is true about injectivity, that you can often just do a little tweak and you get the same thing is true about surjectivity. So can anyone guess, like if you had to rephrase this theorem so that it was true about surjectivity, what would I change? Like what should the statement be such that it's true with surjective functions instead? Does anyone know? F is surjective, right? Yeah, okay, and then everywhere else you put surjective as well, right? So if f composed g is surjective, then f is surjective. Exactly. And so I'd say like recommend trying to prove that. The proof isn't as straightforward, I think. Like it's not going to be a one-liner because you don't have an equation for surjectivity that's as easy to manipulate. So there's going to have to be a little bit of extra work, but just a little bit. But if you want, try and prove the corresponding dual statement for surjective functions and see if you can make it work, okay? Because I think that that's a nice thing to be able to do. And this is an important result. I've definitely seen this exact thing come up in real life, okay? I've had to use it a couple of times. Okay, let's do another one. Now this one, I don't know if you would have seen in 102. This one is crazy important. It's super, super important. I have a feeling this one probably depended on who your instructor was. So show, or maybe I should start by saying what f and g do. So suppose f maps A to B. So let's show that f is injective if and only if there exists a map G from B to A such that G compose F is the identity on A, okay? And remember, in case you're like, what is the identity? So recall the identity map on A is just the thing which sends A to itself, right? It doesn't do anything. It is the function which you give me the input and it doesn't do anything. It just gives it back to you. right? So that's the identity map. So I want you to show that a function is injective if and only if it is left invertible. Okay, and that's what this second part of the statement is saying. It's saying that you are injective precisely if you are left invertible. Okay, maybe that deserves a comment here too. Right? It has an inverse function, but that function only works on the left. You're not guaranteed that it works on the right. The only thing you know is for sure that it works on the left. Okay, let's try this one. Now, there are two directions you're going to have to do here. So you're going to have to prove two things because it's an if and only if. I'm going to start by telling you, I think the converse direction, the backwards direction, is actually the easier of the two. So you might want to start with that one. So suppose that f is left invertible, show that f is injective. I think that's probably the easier one, especially in light of the example we just did. And then the forward direction requires a little bit more work. Okay, so I'm going to give you 5 minutes here. And again, don't hesitate, throw any questions you have in the chat. Okay, so we're going to start off, I think, again, it's if and only if, right? So I've got to prove both directions. And I think that the converse direction really is the easiest because the converse direction is exactly the example that we just did, only with a stronger restriction, right? So again, if we look at the example here that's at the top of the screen, it says, if I know that the composition is injective, then that tells me that the inside function is injective. Well, let's look at the converse. Let's assume that f is left invertible so that there is this function g such that g composed f is the identity. The identity map is certainly injective, right? So that tells us that the inside function is injective and we're done, right? That gives us the opposite direction. Alternatively, you could actually repeat the proof of the previous example, but this time use the fact that you know that this composition is not even injective, is the identity, and you'll immediately get that x is equal to y. Okay, but let me just write that out. I don't expect you to necessarily remember that. So solution. So we're going to do this direction first. So yeah, which one do you guys want? Do you want me to write out just look at the previous example, clearly the identity map is injective, so f is injective, or do you want me to redo the proof? Like, do you care? Which one do you want? Because I'm happy to do either one. One of those is probably less. Okay, whichever one I want to do. I mean, as a mathematician, and I think this should be true of all of you as well, you should strive to do the least amount of work possible, right? So since G composed F equals the identity is injective, F is injective by the previous example, right? Boom, right? So the easiest, yes, I could just leave it blank, but I mean, it really isn't much, right? This is literally just an appeal to the previous exercise. So in that sense, the converse here is a corollary of the previous exercise, which is kind of why I did it first. All right, now the forward direction. Okay, so we have to show that a left inverse exists, which largely means constructing the left inverse. Now, if you can't see what's going on, this is one of these examples where I think it actually really helps to draw out theoretical sets A and B. All right, so let me kind of label this as rough work. This is not part of the proof. So let's suppose this is the set A and this is the set B. And of course, I want to make B bigger, right? Because we're assuming it's an injective map. And let's just randomly draw some lines here like this. All right, so this yellow stuff is the map from A to B. Okay, so what we want to do is we want to define, I'm going to put it in blue. So I'm going to define a map from B to A. And it needs to, let me just scroll up here. It needs to be such that if I do F first, so if I follow the yellow arrows and then I follow the blue arrows back, I just end up where I started, right? So that immediately tells me how to define some of these things, right? This has to do this. The blue arrows, wherever possible, have to just reverse the yellow arrows, right? Because that's this condition that G compose F is equal to the identity. I need, if I go follow the yellow arrow and then follow the blue arrow, then I end up back where I began. And you can do that because because F is injective, you're guaranteed that it's 1-to-1, which means everything on the right has at most one arrow pointing towards it. And so you can just follow it back you can do that. And the thing you'll get is a function, right? You won't have one thing on the right pointing to multiple things on the left. So the only thing we now have to do is figure out what to do with these last 2 points, right? What do I do with these 2 points in order to ensure that the thing is satisfied? So can someone tell me, what should I do with these things? Anyone? Okay, but so this is an interesting thing, because remember, it's a function whose domain is B. So it has to be defined for everything on B, right? And I have to say what the function maps each of these points to. So they do have to go somewhere, right? I do have to have an arrow from them to something, but the question is, what should they point to? Well, they can't map to themselves because I don't know if A is equal to B, right? So I really want to map them to something on the left onto A. Fix an A and map to that? Sure, yeah, let's just, basically what Hyun is saying is like, it doesn't matter, right? Just map them to something. So let's map them all to, for the sake of drawing, I'm going to map them all to this middle point. Like that. Okay, and again, let's check. What's the only thing that needs to be true? It's that if G compose F is equal to the identity, i.e. if I follow a yellow arrow and then I follow a blue arrow, I end up back where I began. Notice that there's no arrows pointing to those circled things on the right. So this is still true, right? G compose F is still the identity. Right? If I follow a yellow arrow and then follow a blue arrow, I always end up where I started, because I never see those two things. There's nothing which points to those circled things on the right-hand side. So there's absolutely no way their definition could possibly affect the left invertibility of F, right? Okay, so the way that we're going to write this down is we're going to say define G from B to A as G of B is equal to A if F of A is equal to B. Oh, you know what? I need to say, damn it. Let me put another line in here before this. Fix some A naught in A. We're kind of assuming that the sets are not empty, because if they are empty, this is a stupid question. So fix some A naught in A, and then we're going to define G from B to A such that G of B is equal to A if F of A is equal to B and A naught otherwise. Okay, so this thing right here, okay, you might have to think about it a little bit, but that thing is just saying map it back to what it came from, right? So you're going to give me G of B, and if it came from something, if there was a yellow arrow pointing at it, then just send it right back where it came from, right? That's what that's saying. And then the bottom line, A naught otherwise, says for everything else, anything that doesn't have a yellow arrow pointing at it, just map it to A naught. I don't care what you do with it, just do something with it. I don't care. And we needed injectivity for this to be a function. This is a function since F is injective, right? Basically, if F is not injective, that green box is not guaranteed to define you a function, because G of B could now be multiple things, right? If there are multiple things which map to B, you don't know what thing to send it back to. And so you'd send it back to multiple things. So you need injectivity for that green square, that green block that I've highlighted, to actually make sense. This is a function since F is injective. And definitely we're going to have G of F of A is equal to A, right? Because the input to G says just send it back where it came from. And that gives it, we're done. Okay, so does that make sense? Any questions about that? And if you're typing a question, keep typing, but I want to ask you the same question. If you wanted to change this example, I assume it wouldn't work if it was surjective, right? Okay. Yeah, so this is the next question. If I wanted to make this surjective, what has to change? Right, because again, there's always a dual, right? So if I want to change the words injective to surjective here, what changes instead? So f is injective if and only if the function has a left inverse, then g is surjective if and only if what? Has a point. Yeah, that's true. So that's the definition of surjective, right? So, but if we want to rewrite this example, rewrite this theorem. So I want to state it as show that f, right? If we read the yellow at the top, I want this to say f is surjective if and only if something happens, right? And what is that thing? What is it? Instead of f being left invertible, okay, but not a two-sided inverse, Tima, because a two-sided inverse only can happen with a bijective function, right? In fact, we probably did learn that in 102. Bijective functions have inverses, right? But that actually is a big hint because an inverse is both a left and a right inverse. So if injectivity gives us the left inverse, then surjectivity should give us the what? The right inverse, exactly. Okay, so try this on your own. Okay, if f is, show that f is surjective if and only if there is a map G from B to A such that, and now switch G and F, right? And becomes the identity on B, so that f composed G is the identity on B instead, namely that f is right invertible. And then you'll see that a function is bijective if it's both injective and surjective, which we know is then equivalent to being both left invertible and right invertible. And it's not too hard to prove that if you're left invertible and right invertible, then you are invertible and that inverse is unique, okay? Okay, now that actually does it for today. I do want to post just a quick little bonus if you want to play around with this. This is a question that I actually gave this. This was a Math 157 term test question way back in the day, and it's the following. And again, if you got to run somewhere, just run. This doesn't matter at all. Okay, we're not going to talk about these things in this course. So F mapping B to C is a monomorphism. If whenever G1 and G2 are two functions from A to B, let me just make sure I'm getting, yeah, such that F composed G1 is equal to F composed G2, then G1 equals G2. Okay. Show that F is injective if and only if F is a monomorphism. Okay. This one's tricky. This one definitely requires a little bit of thinking. It's not obvious. Okay, so you'll have to think about this. It's not impossible, and it doesn't require anything that you didn't learn in 102, or in fact didn't even learn before 102. But you're not going to use G1 and G2 in obvious ways. Sometimes you have to be a little bit clever about how you use them. Okay, so this is a fun little example, but again, it's not a big deal. Monomorphisms actually are important in group theory, and in general, monomorphisms aren't necessarily the same thing as injective functions, but for our purposes, they are. And for those of you who are interested throughout the course, you can ask me, like how are monomorphisms involved in group theory and how are they related? And I'll be happy to kind of bring that up for you. Okay, excuse me. So try this as a problem. Otherwise, that's the end of lecture. Now is my office hours as well. So if anybody wants to hang around and ask questions, I'm more than happy to do it. Otherwise, next lecture on Thursday, we're basically going to take up the worksheet that is online for this reading section. I want to warn you, I think the problems are actually arranged from basically hardest to easiest. So I think question 1 and 2 are actually way harder than 3, 4, and 5. So if you wanted to start them and you're stuck on question 1 and 2 and you're like, oh man, I'm not getting anywhere, this is so disheartening, it's because I think questions 1 and 2 are actually the toughest. So you might actually want to start at question 5 and work your way up. It might actually be easier to do that. Okay. Otherwise, everybody, like I said, this is office hours for me. I'm going to hang around. The rest of you, free to go. Thank you for coming. And I'll see you all on Thursday.